Come back to equilibrium in a bit, but let's take a little bit of an aside. Let's take a look at another topic. Back in Gen Chem 1, we talked about acids and bases. And so let's review a little bit about what we know of acids and bases. So back in Gen Chem 1, we talked about some of the theories behind acids and bases. The very first theory about acids and bases was the Arrhenius theory, and this was put forth by Svante Arrhenius, same guy from the Arrhenius equation, in the year 1900. So about 1900, this is when his theory pretty much took shape. And what he did was define what an acid and base was. He defined an acid as it gives off, or the chemical term is dissociate. It gives off or dissociates hydrogen ion in water. And an Arrhenius base dissociates hydroxide ion, OH minus, in water. Okay. So it was a good start. It was definitely a step in the right direction, but there was a problem with this theory because, and it's mainly the problem is that what he defined as a base, that a base has to give a hydroxide ion in water or dissociate a hydroxide ion, and that's not exactly the case every single time. So the problem with this theory is that not all bases will dissociate hydroxide ions. So in the about 1924, two chemists, Brønsted and Lowry, came up with their own theory of acids and bases based on the work Arrhenius did. So what they did was pretty much keep the Arrhenius part, or the Arrhenius acid part. But so they defined an acid. Brønsted and Lowry defined an acid as a proton donor. So a proton or hydrogen ion donor in water. So in other words, that an acid, when it's placed in water, will dissociate hydrogen ion in water. Now, what they did differently, though, is define what a base was. So instead of saying that a base is going to dissociate and give dissociate hydroxide ions, they said that a base is really going to be a proton acceptor. And so in an acid-base reaction, you're going to have species that are going to give off hydrogen ions, and then you're going to have species that take in hydrogen ions. And in a chemical reaction, you're always going to have them paired up. So Brønsted-Lowry acids and bases come in pairs called conjugate acid-base pairs. Okay. And so the example of something like this would be like, let's say you have a generic acid, which we're going to call HA, and then you've got a base. Okay. This is going to be in equilibrium with the products. And so if HA is your acid, this hydrogen is going to be dissociated. Okay. So this acid is going to spin off, give up that hydrogen, and it'll become A minus. Okay. Now that also means that if the hydrogen, or if the HA is given off that hydrogen, B has to pick up that hydrogen. So then we form BH. Okay. And so if you have HA, which is your acid, B is your base, A minus, if we go reverse now, BH would be your acid because it has the hydrogen. It would spin off and give off that hydrogen to the A minus. So BH plus would be your acid, A minus would be your base. Now to specify whether, what are we looking at, reactants or products, for the right-hand side, the products, we always put the word conjugate in front of it to indicate that these are acids or bases on the right-hand side of the equation. So you have one acid-base pair, you got HA and A minus. So you've got an acid paired with a conjugate base, and then you've also got a base that's paired with a conjugate acid. Okay, let's try a real life example so that way we get away from generics. What if you had hydrofluoric acid, okay, plus water, and that forms an equilibrium. So let's say, well, I just gave it away. Hydrofluoric acid is going to be your acid. And that means if hydrofluoric acid is your acid, that species is going to give off the H plus, and you're going to form F minus. So that's one product. Okay. And so F minus is going to be your conjugate base of HF. Now, what happened to that hydrogen that HF spun off? Well, that was what the water picked up. So water, in this case, acted as a base, picked up that hydrogen, and you formed H3O plus. So this is your conjugate acid. So HF is one acid-base pair. Water and H3O plus is your base conjugate acid pair. Now H3O plus has a special name, and we call that the hydronium ion. And it's essentially water with an extra proton. Okay, now if we were to write the backwards reaction, so if we were F minus plus H3O plus is in equilibrium with HF and water, it becomes a little bit easier. Perhaps you can see this a little clearer, that F minus is going to pick up the hydrogen from H3O plus to form HF. So in this case, F minus is going to be your base, and HF would be your conjugate acid. H3O plus, since it's giving off the hydrogen, is going to be your acid, and then H2O is going to be your conjugate base. Okay. What if, let's write another Bronsted-Lowry acid-base reaction. This time I'm going to use something called methylamine, which is a methyl group plus an NH2. Okay. So here's your base, and it's going to react with water. Okay. So the way this works is that we're going to use that lone pair of nitrogen to pick up the extra hydrogen from water. Okay. And so we form CH3, NH3, and OH minus. So if methylamine is your base, then methylammonium ion is going to be your conjugate acid. And if water is your acid, that means hydroxide ion is going to be your conjugate base. So it's kind of nice. You always have an acid and a base on the left-hand side. You always have an acid and base on the right-hand side. And if you got an acid, it's going to be paired with its conjugate base. If you got a base, it's going to be paired with its conjugate acid. Okay. All right. What if we used a different base? Let's try another base. Let's use fluoride ion. Okay. So you have fluoride ion, you got water. In this case, one of the pairs of electrons in the fluoride is going to pick up one of the hydrogens. And so you get HF plus OH minus. Okay. So again, F would be your fluoride, would be your base. Water, because it's donating the proton, would be your acid. That means HF, since it's an acid on the right-hand side, we call this conjugate acid. Hydroxide ion, conjugate base. Okay. All right, so what features does a Bronsted-Lowry base contain? Well, what features? In order to be a Bronsted-Lowry base, you must have at least one pair of electrons. Okay. Now I am writing into the example equation, but let's take a look at some of this. So specifically this last problem, fill in the species on the missing table. So you've got the first row is your acids, second row are your bases. So if you've got water as an acid, what is its conjugate base? Well, deprotonate the acid or the water, you've got hydroxide. If Cl minus is your base, then protonated version, HCl, is going to be your acid. So that's the difference. If you got a base, protonate the base and you got the acid. If you got the acid, take a hydrogen away and there's your base. So if you got an acid like HNO3, the base, the conjugate base, would be NO3 minus. Or if you have NH3 as your base, the acid would be NH4 plus.